All right. So we talked about inner products last time, and we're going to say a lot more about them today. As part of the discussion for inner products, I'm going to talk about norms, which is a way of measuring magnitudes of elements in a vector space and distances between elements. So remember I said that with inner product, we are entering a phase in our discussion of vector spaces where we introduce geometry into the picture. So this is where that happens. And then, once we're done with this discussion, I'm going to move into the four fundamental subspaces of a matrix. Subspaces of a matrix. I apologize for this chalk that whoever used it before me decided to pick something that doesn't erase well. Okay, so let me just review what we said. We said that inner products are functions from, so on a vector space. Our vector space is nu. So they're functions of nu cross nu, meaning it takes a pair of elements from nu and maps it to R for our case. And when you go to 16b, that R is going to change this to the set of complex numbers. And the inner product has certain properties. For example, we have commutativity. We have distributivity. So if I take the inner product of x with the sum of a couple of vectors in my space, that's the same as saying that I can take the inner product of x onto the first one, y, and the last one, z. We had the scaling property, that if I multiply one of the vectors by alpha, I can simply put out that alpha. Here, alpha is a real number, and this relationship must hold for all vectors x and y in my vector space and all scalars alpha. And the last property was that if I take the inner product of any vector with itself, I'm going to get a non-negative quantity with equality if and only if and only if x equals the 0 element in my vector space. So those were the properties of the inner product. And if we're living in the space of, so if our vector space is R, say Rn, then we can define the inner product in this way. So now I'm going to put the underscore because now I'm talking about Cartesian vectors here. And this is simply x1. Well, let's write it out just so that everybody's on board. y1 through yn. And that's x1, y1 plus all the way to xn, yn, which I can, of course, write in summation form as small n going from 1 to n, x small n, y small n. Okay, so this is how we're going to define our inner products for our Cartesian vectors. All of this we've done, and it's review. The other notion I introduced, now I'm going to say a lot more about this today, namely in terms of, in particular in terms of projecting a vector onto another and how we define angles between vectors and so on. The other notion I introduced at the end of the last lecture was that of a norm. So again, nu is my vector space. And let's say x is some element in my vector space. The norm of an element x is a function that takes an element in the vector space and maps it to the reals. And this function must satisfy certain properties. So one of the properties is that it must be non-negative with equality what? If and only if x is 0. So the only way the norm of an element in my vector space can be 0 is if that element is the 0 element in my vector space. The other one, as you can get inspired by what we did there. The other one is if I scale any element in my vector space with an arbitrary scalar, what should I get out? Huh? Times the magnitude, or times the norm, and absolute value of alpha. It can't be just alpha, because remember, the first property says you have to have a non-negative quantity. So alpha can be an arbitrary real number, so it can be negative. And to account for that, we put an absolute value sign here. And the other property is if I take the norm of the sum of two vectors in my space, that's less than or equal to the sum of the individual norms. Now, each of these has a name. This is, of course, non-negativity. The second one is the scaling property. And the last one you told me last time is the triangle inequality. So if I have a vector x and I add to it a vector y, the sum of the two is, of course, this, right? Actually, I should label it here. Let's use different colors. So this is x plus y, and this is y. Okay? So the triangle inequality simply says that when you look at this triangle, the length of the sum of the two vectors, the length from here to here, which is x plus y, is less than or equal to the length of x and the length of y. So geometrically, that's how you picture it. Now, there are different kinds of ways we can define a norm in any vector space. I'm going to give you a few examples of them. And then we'll fixate on one for the rest of the semester. So, examples of norms. Examples of norms. One is called the L1 norm, and that's where you add, so now I'm going to restrict my vector space to be Rn. And that is the sum of the components of the vector x, absolute value. Okay, so if my vector x consists of components x1 through xn, The L1 norm is obtained by adding the absolute value of each of the components in a sum. And I'm not going to go through the process of showing you that this definition of norm satisfies these properties. If you're really gung-ho about this stuff, you can try it at home. Basically, whatever you know about absolute values is going to kick in, because the absolute value of a real number is a norm for the vector space of real numbers, and it satisfies all these properties. So by extension, you can show that this is also a valid norm. Another kind of norm is called an LP norm. And the LP norm of a vector, I should have put an underscore here. The LP norm of a vector is the sum of the absolute values raised to the power p. Now, all of these, now some of these might look bizarre to you, but they all have applications in dynamic systems and control. A special case is when p is equal to 2. That's what we're going to fixate on for the rest of the semester, although there's another example I'm going to give you after this. But we're going to come back to this case. So the special case is the L2 norm, which is, I should have put a p here, 2. And because we're going to fixate on the L2 norm for the rest of the semester, I'm going to drop the subscript 2 in no time. Okay, so from now on, whenever I talk about a norm, I'm talking about or after I give the last example, anytime I talk about a norm, I'm talking about a 2 norm. So the 2 norm, obviously, is when you substitute for p the number 2. Now, can you tell your neighbor if there's a special relationship between this definition of norm, this is how we're going to describe things. Actually, I should have put a, yeah. And the inner product that we defined. By the way, I should actually correct myself a bit and say that from now on, we're going to refer to this as the magnitude squared, because you may have noticed that that's magnitude squared. OK, so is there a relationship between this particular norm and what we defined as the inner product? And if so, what is it? Are you done talking? OK, I'll take a volunteer. It's the inner product of the vector with itself. It's x transpose x. And this, of course, is the magnitude squared. So the magnitude, or the actual length of the vector that you're used to talking about, is the square root of this. But of all the p norms, this is the only one that we say is induced by the inner product. Inner product. So if you ever hear the term induced norm, it's usually the norm that's induced by the inner product in whatever space you're living in. The space we're going to be living in is the Cartesian n space, or m space, whatever this number is. It's a vector with a bunch of components. And our inner product is the transpose of a vector with itself, as far as the 2 norm is concerned. So this is going to be what we're going to use for the rest of the semester. I'm going to give you one last example of a norm. And that's the L infinity norm. And the L infinity norm for a vector is the maximum of the absolute value of the individual components. That's also a valid norm. Again, I'm not going through all the processes of showing that these definitions of various definitions of norms satisfy the properties that we described, but they're not very hard to show. So just to give you a sense of, LP norms are more difficult to describe at the level of this class, but the infinity norm, I think I can put it in a language that you might appreciate. So suppose you're trying to design in a small town, maybe in a rural area, where to put your fire station or where to put your hospital. One way you can do it is by looking at the individual distances of the maybe 500 homes in the town to the location you're trying to place that fire station, and say, okay, I'm going to place this fire station so that the magnitude squared of the vector of the distances between the location and each of the n homes in my town is minimized. So that would be an optimization problem involving minimizing the L2 norm. Okay? Now that strategy might work well if you're trying to place a bank in that town, or a grocery store. But for an emergency vehicle situation, or an emergency center situation, that optimization can be fatal to the poor guy who's very far away, because you can minimize the magnitude squared of a vector and still have one of the components be larger than what is reasonable or safe. So in that situation, because the ambulance can't, if the guy falls down, there's an emergency situation, you need a basic minimal or maximum amount of time that you need for the ambulance to get there. So that would be a situation where you would want to minimize the L infinity norm. You're going to decide what the maximum safe distance is, and you're going to place let's say the fire station at a location such that if there is a fire, the maximum time it takes is within your specs. So that would be a case where you do an optimization over L infinity norm. But we're not going to deal with that in this case. I just wanted to mention that just so you know I'm not throwing these at you for the sake of it. What we're going to focus on is the 2 norm from now on. Okay, so the norm also helps us determine distances between vectors. So let's go back to the 2 norm. Any questions on what I've done before I move on? Okay, cool. So the norm that we're going to use is also going to tell us the distance between 2 vectors. So if I want to measure it this way, this would be, is this x minus y or y minus x? Let's see if you can remember. If I put the arrow here, x plus y is going to be the other diagonal, right? So I'm not doing that. This is going to be x minus y or y minus x. Tell your neighbor. Let's see how much you remember. What's the verdict? Y minus x? X minus y? So what did we say? So those of you who said y minus x, which one takes the plus sign? Which one takes the negative sign? In front of which one is the negative sign? Y. Which one takes the arrow? Y. And the one that takes the arrow has the plus sign. We worked this out several lectures ago. So this is y minus x. So the norm gives us a way to measure that difference, gives us a way to measure the sum. So we have a notion of distance in our vector space among elements. In the definitions that I gave you for a vector space, we didn't have this notion. We just had an algebraic structure governing our vector space. We had no geometry defined. Now we have a geometry defined, and we're going to hash that out even more. So let's go to one of the most important rules, which is the cosine law and inner products. I'm going to do everything in 2 dimensions. The extension to higher dimensions is fairly straightforward. So let's say I have 2 vectors, A, which has 2 components, A1 and A2. And I have another vector, let's say B, which has 2 components, B1 and B2. And I can drop down to the axes and mark B1 and B2. And I'm going to mark this angle from the positive horizontal axis as beta. And I'm going to do the same thing with A. So this is A1, and this is A2. And this angle I'm going to call alpha. And I'm going to define a third angle, which is the angle between these 2 vectors. I'm going to call that theta. And theta is alpha minus beta. OK? So that's my picture. Are we all here? I've got 2 vectors, A and B, each with their corresponding components. The components, of course, are the orthogonal projections onto the horizontal and vertical axes, respectively. Each one of them makes an angle with the positive horizontal axis. So I'm going to call this one beta and this one alpha. And the angle between the 2 vectors I'm going to call theta. So that's the difference between alpha. So if I subtract beta from alpha, I'm going to get theta. That should be clear from the picture. OK. Now, what happens when I take the inner product of these 2 vectors? What is it in terms of A1, A2, B1, B2? What's the inner product? This is my definition of inner product. What is it in terms of the components? A1, B1 plus A2, B2. Now, can you give me what A1 is in terms of the magnitude of the vector A and the angle that it makes with the horizontal. And can you do the same thing with A2, B1, and B2? Can you work with your neighbors and tell me how you would get if I tell you, so let's say B and A, you know, and the angles you know, what would be the corresponding components here? What is A1? While you do that, I erase some boards. I'll take my last volunteer for the day, and then we'll start picking people. No, you've been answering too many. Anybody? You are? Bill. Go for it, Bill. Magnitude of A. Cosine? Alpha. So this is like maybe even middle school geometry, right? So you've got a triangle, and this side is the length of this side times the cosine of the angle, alpha. And what about A2, Bill? Sine of alpha. And this one? Cosine beta. And magnitude of B, sine beta. Okay. Now, can we plug these into the definition of the inner product of these two? In other words, can I write the inner product in terms of these four right-hand sides? Can you walk me through this, Bill? Magnitude of A times the magnitude of B. This is times cosine alpha, cosine beta. This whole thing is A1, B1. Right? I'm multiplying A1 by B1. That's how I get this term. Plus magnitude of A, magnitude of B, sine alpha, sine beta. Great. Now, can you simplify those terms, Bill? So I clear out the magnitude of A and B. I factor them out. And let's see what we get. So the inner product of A and B is the magnitude of A times the magnitude of B, cosine alpha, cosine beta, minus sine alpha, sine beta. And I think we can spare you the walk to the corner of useless information. This is what? Cosine of? Alpha minus beta. And what do you know about alpha minus beta? It's theta. So, yeah. Huh? Oh, sorry. This is a plus. Now it makes sense. Okay? So maybe I should have walked to the corner of useless information to remind myself. So what do we have? We've got the inner product of A and B, two vectors, is equal to the magnitude of A, the magnitude of B, times the cosine of the angle between them. This is the cosine law. And this is great because I can now define angles between vectors. I can define orthogonal vectors. I can define collinear vectors. Right? And in fact, I'm not restricted to the inner product for Cartesian vectors in a different vector space. Any inner product that I define that's a valid inner product, along with the corresponding induced norm, will satisfy this property. So I can be living in the vector space of continuous time functions, or periodic functions, or whatever, random variables. For all of those, I can define orthogonality. And the way we can see that is by keeping the cosine on one side and writing everything else on the other. So if theta is between pi over 2 and 0, then the inner product is positive or negative? Positive. And if it's between pi and pi over 2, it's negative. And if theta is pi over 2 exactly, then what can we say about the inner product of two non-zero vectors? 0. In fact, this goes both ways. So we say two vectors are orthogonal if and only if their inner product is 0. So when you take the inner product of one vector onto another, if you get 0, you can conclude that those two vectors are orthogonal. And orthogonal vectors play a very important role in linear algebra and in engineering. In fact, there's a topic that we'll come across later in the semester where we take a set of linearly independent vectors that are not necessarily orthogonal, and we orthogonalize them. And it's all based on the definition for inner products and what they mean geometrically. Any questions on what we've done? Do you need a break? Banza! Okay, take a break. Next, I'm going to talk about projections. Actually, before projections, I'm going to talk about one inequality that's very important, and it keeps showing up in various areas in linear algebra and engineering. And that's a direct consequence of this cosine law that we found. So we showed that cosine of the angle between two vectors is this ratio, where the numerator is the inner product of the two vectors and the denominator is the product of the norms. If I take the absolute value of each side, what do you know about the absolute value of the cosine of an angle? Between 0 and 1. So can you come up with an inequality for this, the magnitude of the inner product? On this side, it's not too hard to see that it's always greater than or equal to 0, with equality if A and B are orthogonal. Well, 0 or orthogonal. And on this side, what do you have? Less than or equal to what? Product of the norms. This inequality is called the Cauchy-Schwarz inequality. Actually, there's a third person involved. May as well introduce the poor guy who's always left out. Inequality. There we go. But very often it's just called the Schwarz inequality, and also very often it's called the Cauchy-Schwarz inequality. I had to look at my notes to remember his name, or to remind myself of his name. So I'll come back to this inequality right after I talk about projection, because there's another geometric interpretation to this inequality as well. But right now, the geometry that we use to derive it is what we know about the cosine. Cosine is always between -1 and 1. When you take the absolute value, it's between 0 and 1, and that's all that we applied to the cosine line to come up with this inequality. Okay? All right. When do you have equality? Tell your neighbor. When cosine is what? 1 or? Or what? You need to talk more. When do you have equality? Not when they're orthogonal, right? Because if they're orthogonal and they're both non-zero vectors, there's no way you can have equality. One side will be 0 because the inner product will be 0, and the other side won't be. So when do you have equality? Just look at this equation. When would these two sides be equal in magnitude? When the cosine is what? 1 or -1. And when does that happen? When theta is 0 or pi. So with equality, if theta equals 0 or pi, which means that your two vectors are either at an angle of pi or are collinear in the same direction. Theta equals 0. Okay? So that's when the projection is, which I'm going to get to in a moment, is perfect. The theta doesn't diminish anything. All right. Let's go here for the next topic, which is projection onto a vector. And this is used a lot in estimation theory. So the application is estimation. And I'm going to describe the problem in this way. So let's say I have a vector A, okay? And I have a vector B. And I tell you, hey, Joey, you're only allowed to walk along the vector A. Find the best approximation. So we're stuck along A. All we can do is march up and down this line. Determine the best estimate or approximation. And I'm going to call it B hat to the vector B. Where would you stop? Talk to your neighbor. Mark on this axis, defined by A, the point that would correspond to the best approximation to B. And then we'll hash out the mathematics of it. Right now, I just want you to come up with an intuitive picture. Where's my red chalk? So what's the answer? Oh, Bill, you get to pick the next person. Red shirt. Yes, laptop. You are? John. Drop a perpendicular to A. And this would be B hat. Right? That's the best estimate. Geometrically. Now, why is that, John? That's a circular argument. What is it that you're minimizing? Let me ask you that way. You've got to minimize something, right? You can't get B exactly. You agree? Are we all agreed on that? We can't get B exactly because we're stuck here, and B is outside the span of A. So that's the important point here. B is not in the span of A. So whatever we come up with is not going to be an exact match to B. The best we can do is come up with the best approximation. So whenever we talk about approximation or best, anytime somebody asks you what's the best, blah, blah, your first reaction should be a question. Best in what sense? According to what optimality criterion? Okay? So what is it that we are optimizing here? If I'm not getting B exactly, then there's got to be an error. Can you show me the error in this picture? Is there an error vector that you can show me? Oh, there's my red. What would a good error be? Error would be, that would be a great error, 0. But I can't have that here. Talk to your neighbor. Define a reasonable error. It's staring at you actually in this picture. Why don't you talk to your neighbors, John? Okay. Can you show me how to draw an error? And then maybe we'll define it, or define it for me and then we'll draw it. Yeah. The end of B and any part of A, right? So if I had picked, so in this case, the error is here. So what would that be in terms of B and B hat? B minus B hat. This is B hat. This is B. B minus B hat is the line that adjoins the end. And the one that's taking the arrow is the guy who doesn't have the minus sign in front of it. So this is the arrow. So this is my error vector. Now, if I had been sitting somewhere else along the A axis, where's my yellow chalk here? So I could have said this is my, would this have been a good estimate? Would this have been a good estimate? Huh? So why is it that we're picking this guy? Because it minimizes what? The error length, the norm of the error, which in this case happens to be the square of the norm of the error. So by looking at this picture geometrically, the optimal B hat is the one for which the error vector is minimized. And it's the same as saying the error squared is minimized. Why is it that that particular one is the minimum, the red one? What's special about this vector, John? It's perpendicular. And you know from high school, or maybe even middle school, or whenever it was you studied Pythagoras' theorem, is that this side is shorter than this side, than the hypotenuse. This would be a hypotenuse, right? Each of these yellow ones that I've drawn would be a hypotenuse in a right triangle. This is the one that's the shortest. So here's our optimization problem then. I'm going to formulate it this way. First of all, so our optimization problem is this, or estimation problem, whatever you want to call it. I've told you that you're stuck along the subspace spanned by A. In other words, your estimate, whatever it is, has to be some scalar multiple of the vector A for some scalar in R, right? That's the only way I'm going to stay in that subspace. So my best estimate is sitting along that line defined by the vector A. So whatever my best estimate is, it's got to be a scalar multiple of A. My task is, or your task, is to determine alpha such that what, people? The error, which is defined as B minus B hat, has minimum norm. That's our optimization problem. All estimation and optimization problems in one way, shape, or form boil down to this, that you're doing a projection onto a subspace. Later in the third module of the course, we're going to graduate from a simple single vector, and we're going to project onto a subspace spanned by a bunch of these A vectors, A1 through AN. But right now, we'll keep it simple. Right now, our optimization problem is that we want to find the best estimate along this space spanned by A, which is mathematically written this way, such that the error is minimized. But you've already told me how we're going to minimize that error. By ensuring what? I'm going to go here. We minimize the error by enforcing what? What must be true about the error? It's perpendicular to A. So we know from the geometry of this picture that if we ensure that the error vector is orthogonal to A, we're home free. We can basically, applying this will get us the alpha that we want. Well, what does it mean for epsilon to be orthogonal to A? The inner product of epsilon and A must be 0. There's nothing fancy that's happening here. If you understand triangles, Pythagoras' theorem, hypotenuse, sides, you've got it down cold. The rest is just so what is my epsilon? The error vector is B minus B hat, and I'm taking the inner product with A. What do you know about the properties of the inner product that allow you to massage this expression? Remember those properties? These properties. What do I do here? B inner product. Go for it. You are? Daniel. B inner product with A minus B hat inner product with A, and this must be 0. What do you know about B hat, Daniel? But B hat is? No. How do you express B hat? We have an expression for B hat. Alpha A. So you plug that into the second term. So now you have BA minus alpha A inner product with A is equal to 0. Well, let's keep the 0 until the end. So the first term is the first term, BA. What's the second term, Daniel? Again, one of those properties. What do I do with alpha? Take it out. A equals 0. Can you all solve for alpha, please, and tell me what B hat is? I have my equation. I have only one unknown, that's alpha. All I need is one equation. I have my equation. How did I get my equation? By enforcing orthogonality. Why am I enforcing orthogonality? Well, that's the one that's going to give me the shortest error. So what is alpha? Daniel, you want to finish the story? It's the inner product of B and A. A and A. And I got OCD. I don't like B before A. So I'm going to put A, B. It's up to you, whichever one you want to keep. Okay, but the point is that B hat, we now have a B hat, which is alpha times A, which is A, B over A, A. Actually, I've got to be careful because one of these forms will give me what I want more easily. Yeah, I'm going to keep that one. And this times A. This is my best estimate. Any questions? I'm going to give you about, well, first let me see if there are any questions. And I'm going to make you explain to your neighbor what we just did. Quickly go from here to the end. What did we do to come up with this estimate? But any questions? Yeah. A dot A equal to 1? That's a good question. I didn't specify what the length of A was, right? Which is why this is showing up in the denominator. Because if you want to think about it this way, this is A, B, and I can write A, inner product A, as the magnitude squared of A. So I can write A magnitude, right? Isn't the product of these two just A dot A? Right? It's the magnitude squared. So I'm going to write magnitude squared in this way, and I've got my A here. What kind of vector is this? A unit vector. So if A starts out being a unit vector, then you're golden. You don't even need this denominator. But because I didn't specify that A is a unit vector, this had to show up. So what this expression says, so this is a unit vector in the direction of A. So how many units do I need in the direction of A? That's given by this ratio over here. But these two are equivalent. If I don't tell you what A is, if I don't tell you what the length of A is, you're going to have to keep these things in the denominator. If A is already a unit vector, well, this is 1, and that's a unit vector already. So your coefficient will simply be the inner product of A and B. Okay, now spend a minute just explaining what we did, starting from this picture all the way to the expression, and make sure each of you understands what just happened. Are we all good? The key is basically that picture that I drew with the vectors. If you understand that picture, everything else is just a corollary of that. Any questions? Okay, I'm going to say one more thing about this expression. And then we move on to the 4 subspaces, and that obviously has to continue next time. So I'm not going to rush through that. I can rewrite this expression in a different way so that you get another interpretation of what we're doing here. A inner product B is A transpose B. And this one, of course, is A transpose A. And the whole thing is multiplying A. Now, do you agree that this is a scalar? It's a scalar over a scalar. So does it, I'm going to do something weird. I'm going to take this scalar to the right side of this vector. Does that matter? Good. So I'm going to write A here. And I have A transpose B over A transpose A. Okay? Now, matrix vector multiplication, a long time ago, you thought it was a very boring property, that associativity. Here we've got a whole bunch of matrix vector multiplications, essentially. That's what it is, right? It's just that our matrices are 1 by something. So I'm going to use the associativity property and group these together. And I'm going to write this as B A. This is a scalar, so I can simply write that as A transpose A inverse. And this is an A transpose. That's an A transpose. Scalar, I brought it to the numerator. I just wrote it as inverse. I stuck it between these two. And my claim is that when I look at this, this is a matrix that takes the vector B and does what to it? Projects it onto the axis defined by A. So PA, which is A transpose A inverse A transpose, is a projection matrix onto the span of A. So you give it any vector. In this case, we've given it the vector B that is not necessarily sitting in that subspace defined by A. And this matrix will project it down just to the right place that's closest to itself. So later on, when we get to the 3rd module of the class, we'll be dealing with more than one vector. Later, okay? And we have a vector B that's not in the span of the columns of A. And you will find later that the best estimate B hat will be the matrix that projects onto the span times B, where the projection matrix has the identical form. A transpose A inverse, A transpose B. And those of you who've taken linear algebra before should recognize this as the solution to the linear least squares problem. But we'll get to this later. Right now, I want you to only look at this. And for a single vector projection, this is sufficient. But notice the similarity between the forms. There is a reason why I went through these acrobatics to rewrite what seemed like a very simple scalar multiplication of the vector A in this form. So that's a projection matrix. This is a projection matrix. And what it takes, what each of them does, is that it takes whatever vector you give it and gives you the closest point along the subspace defined by small a here and the columns of A in this case. Am I out of time? How much time do I have? 4 minutes. Ah! 1 minute for each subspace. Woohoo! Just kidding. Okay. So for, whoops, I don't want that. For fundamental subspaces of a matrix A. You've actually come across them already, except for one of them. So I will introduce you to these 4 subspaces, and we'll say more about them later. You've already seen equations of this form. When you multiply a matrix by a vector x, and you get the 0 vector. So there is this space associated with any matrix called the null space of A, which is the set of all vectors in, let's say, A is m by n. So it's got n columns, and each of these is in Rm. So this is the set of vectors in Rn such that Ax equals 0. In other words, you feed these vectors into the matrix A, and it spits out the 0 vector. You already know that if the columns of A are linearly independent, then the only element or the only vector in the null space is the trivial 0 vector, right? So now, what if you look at A in terms of its rows? I'm just going to stop at the null space, and then we'll deal with the rest later. So if a vector x is in the null space, and I look at A in terms of its rows, what does that say about, oh, sorry, Ax? When Ax is equal to 0, first of all, what is Ax? What's the top entry here? Remember the row vector picture? Isn't it alpha 1 transpose x? All the way to alpha m transpose x. This is the row column vector multiplication picture. And we're saying that these are all zeros. What does that say about x and the row space? The rows of A. Huh? So I'm saying this is 0. But what is this? Isn't it just simply the orthogonal? This is the inner product of the first row with x. Second one is this inner product of the second row with x. So all of the rows of x are orthogonal. All of the rows of A are orthogonal to the vector x, which means x is orthogonal to alpha 1, alpha 2, all the way to alpha m. We have this interpretation now because now we know inner products and we know what angles between vectors are all about. Okay, I'll pick up on this on Thursday.